Okay, so the way we play Calculus Jeopardy is just like normal Jeopardy. Okay, but I'm doing this to illustrate an important point here. We're launching into part 2 of our class. This is we've sort of completed, or close to completed. I know some people still have some things to wrap up. We'll be in the lab and you'll have a chance to do that. But we did differential calculus. You know, we worked with derivatives, and you guys are good at derivatives. You know how to take derivatives, complicated derivatives. You've worked with some big applications of derivatives. Now we move on to the other part of the course, which is related but very different. This is called integral calculus, and you'll see though that it's really strongly related to what you've already done. So knowing what you already know makes this much easier. Okay. So who'd like to be our first contestant on Calculus Jeopardy? No. It's not hard. It'll be no problem. Right here. Yes, sir. Choose a category. Okay. You got it. There it is. Okay. Omnipotent. That's a power function, right? Yeah, okay. So my derivative is 3x squared.
We're going in reverse. Oh, am I supposed to answer?
Yeah. Let's hear the. We need the theme song.
What is
in the question?
Nice.
x to the what? What is x to the cube? X cubed?
What is x cubed? I'll give him credit for that. Excellent. And the answer is, what is x cubed?
That sounded like if you have
Okay, or what is the function x cubed, or something like that. Okay, somebody else, the thing is, we could play this game all day long with just these 2 questions. Somebody else want to give me a different answer that would also be correct? X cubed was probably the easiest answer. That was that was the one that everybody would think of first. But what's another one? X cubed plus 1. Sure, we could have also said, what is x cubed plus 1? Or any other constant, right? Right. And so, okay, makes sense? Okay, very good. So our general solution to this, then, does anybody want to give me the all-encompassing general solution that would incorporate every conceivable answer? What is?
plus or minus.
Say, okay, that's good. What did you say? Plus or minus n, something like that. Okay. Yeah, now we're on to something. We could say, if we wanted to incorporate everything in there, we could say something like, what is x cubed plus c? What do you suppose c means? Any constant. Any real number constant, right? Okay. Okay, so anybody want to try this other one here? What do you think? Elizabeth. Why not? Why not? Sign of the times. My derivative is cosine x. So see if you can give me the most general solution to this one.
Sine x plus c.
Sine x plus c, but, what did we forget to do?
Plus or minus.
No, you're right, but this is Jeopardy.
Oh, what is?
What is, got to be written in form of question, of course.
Oh, double Jeopardy, double Jeopardy,
Sorry.
double
What
Jeopardy.
is sine x plus c, okay? Good, and so really Calculus Jeopardy illustrates what we call the process of anti-differentiation, okay, which is just reversing the derivative. Okay, and that doesn't seem too bad, does it? Now that's the principle upon which all of the second part of the course is based, is this idea of anti-differentiation. So for example then, we could take this example with the x cubed, how about? And we could say this, if f of x equals 3x squared, then capital F of x, that's a lowercase f of x up there. If capital F of x equals x cubed plus c, we would say that that's what we call the general form of the antiderivative.
Capital?
This one right here, yes, this is what we call the antiderivative, the general form of the antiderivative, okay? Why do you suppose we call it the general form, obviously?
What is this everything?
Because it encompasses everything. General means not specific, right? So this would work in all situations. Okay, so let's look at maybe a graphical example of this. What if we take something a little bit simpler? What if we take something like, how about we start off with the Jeopardy question? Y prime equals 2. Okay. The antiderivative of that is the Jeopardy answer. So what would it be?
What is 2x?
Okay, and if this is written in terms of y prime, then we would write it as y equals 2x plus c. Yeah, exactly. Okay, now what does that look like in terms of a graph? This is the general solution, right? And so c could be anything. I mean, there are an infinite number of graphs I could make, but how would you describe all of them? They all have a slope of 2. These are just lines with a slope of 2, aren't they? Right? And so if we were to graph these things, they really just look like, they just look like that, or like that, or like that, right? Now, what we've drawn here, these are just what we call, and the terminology is I think really good that we use to talk about this stuff. This is what we call a family of curves. And family of curves because they're all related, right? They all have the same slope, okay? Each one of these individual curves that we've drawn, each member of the family is what we call a trajectory. Okay? But the general solution means all of them, all infinity of them. Okay, but what if we want to single out a particular one? Okay, then we could maybe say something like this. Let's say that this is the original Jeopardy question, but we're going to specify that when x equals 0, y equals 2. So there are an infinite number of curves up there, but those curves do not intersect, do they? Right? And so if a point lies on one of those trajectories, it can't lie on any others, right? So when x equals 0, y equals 2 is going to single out a particular trajectory out of that family. Yeah, and what would be the answer to that one, to this revised Jeopardy question? Y equals 2x plus 2. Yeah. Okay, so, that is what we call a particular solution, for obvious reasons, because we were particular. We added the additional criterion that, this is the family defined in blue, but here's a particular condition defined in green that singles out one trajectory. So this part right here we sometimes call, we describe this in a couple of ways. We describe this as either a particular condition, right? So we've added a condition that has to be met that isolates one trajectory, or the other way we describe that sometimes is as an initial condition. And of course, initial just means what? Yeah, starting condition or something. Now, the physicist in me really, I like this, but this says something more specific to me. Math books sometimes, I think, misuse this a little bit. I think your text does. Initial condition really ought to imply what value do you think for the independent variable?
0.
0. Yeah, it ought to imply 0, because typically, like in engineering and in physics, the independent variable is usually what? What do you think? What do we usually look at when we look at the evolution of a system? What's usually, we track it with respect to what? Time. Yeah, usually we're looking at force as a function of time, or we're looking at energy as a function of time, or something like that. Man, Campbell's on a roll.
I know it all. We're done here.
I'm glad you got that script I sent you last night. That's good. You read it? That's good. And so if we're doing something like that, if we're looking at, say, we want to look at the arc of a projectile, or we want to look at force as a function of time during a collision or something like that, well, then it makes sense that initial means when we start the stopwatch, so that's at t equals 0, right? Like I say, a lot of times in textbooks with the math, they don't do that. I mean, the initial condition could be defined for any value of x or t. So I really like this terminology better, unless it's specifically a value 0, but that's not the way the book deals with it. I mean, but you later on in life, if you go into engineering or physics, or you'll probably see a little more specific treatment of that word initial. Okay, so how could we be a little bit more rigorous about this process of getting to the green solution here, right? You guys told me because it was a line and it was easy. We had drawn a picture up here with trajectories of the graph. But what if this were a harder function? We're going to get to deal with more and more complex functions. We're going to eventually we'll add some exponential functions and logarithmic functions and things like that. What do you think?
Chelsea, you like start from a double prime.
You could, yeah. In fact, what's really cool about this, and I'm really excited about this part of the class because we get to do some other really cool physics stuff. We get to, very soon, we're going to get to derive, for you physics types out there, we're going to get to derive the equations of motion, or the kinematic equations, I should say. Because those are just kind of given to you and you use them, right? I mean, but that plug and chug mentality is just, that's not, we don't, it'd be nice if we knew where that stuff came from. Where does the for example, when you look at equations like this right here, when you guys, I don't know how your book writes it, but something to this effect, x as a function of t equals 1/2 at squared plus v naught t plus x naught, or maybe you write it as delta x minus x naught, displacement, I'm not sure. But in your physics classes, you've looked at this stuff, right? Where's that come from? Where does that mysterious equation come from? Well, we can derive that now from just basic principles here shortly in calculus, which I think is really cool.
All this other stuff wasn't printed off the script.
Oh, it wasn't? Okay. Sorry. My ass is a little bit here. Sorry.
You lost.
Sorry. Okay, so so let's go back and let's revisit this last question that we just did and see if we can come up with a little more systematic way of doing this. The way this might be written is, when I'm asking for a particular solution, it would be something like this: y prime equals 2, and we're going through the point. So we have the initial condition or the particular condition 0, 2. Another way of saying that would be f of 0 equals 2, something like that. They all say the same thing. This just gives us a point on the xy plane. This is a little different way of writing that, but it all says the same stuff. Okay, how do how do we come to that answer that you guys came to earlier where you said the answer is 2x plus 2? Okay, first things first. Okay, the first step is, let's write out the general solution. So what is the general solution to that calculus Jeopardy question? Okay. And if we want to quit thinking of this in Jeopardy terms, really what this is called, by the way, and this, I was going to kind of describe this a little later, but now that's what we call a differential equation. And we can describe it in more precise terms, but for now, that's all we need. It's a differential equation, and what, you might ask, in the heck is a differential equation? Differential equation is simply an equation that involves one or more derivatives. That's it, okay? And we're going to solve this differential equation. Okay? And that's, when we're done with it, I'm asking you to tell me, what do you think it means to solve a differential equation? All right, so you've already told me that the general solution was y equals what? X, 2x plus c. 2x plus c, okay. So that's the general, that's the general form or the general solution. It's the solution in general form. Okay, so how do we find the value of c then? Without just thinking about it or using a graph. Plug it in? Yeah, plug the point in, exactly. So what we're going to do is we're just going to evaluate the general solution with the particular conditions. Does that make sense? So if we evaluate y at 0, 2, we get what? 2 equals 2 times 0 plus c. Solve for c. So what's c? 2. And that tells us then that the particular solution is just y equals 2x plus 2. Okay. Make sense? That's really all there is to it. Now, we're going to come up with some rules for this, but for now, you're just kind of finessing your way through it, and you're just thinking, okay, you really are just kind of playing calculus Jeopardy. And that's okay to do with certain functions. With a lot of the functions that we know now, you literally can just kind of think backwards, can't you? Right? But it does get a little harder than that, and then we need some general rules to apply. Some, like, just the equivalent of our derivative rules, we will have these antiderivative rules. Okay, so what's our notation for this then? Okay, so if we really want to solve this thing, if I want to be able to write these things down in an intelligent way, how do we go from something like that to our solution, capital F of x, which is the antiderivative? Okay, well, here's how you do it. Here's kind of the process we follow. Oh, I guess before we jump into this too, what does it mean to solve a differential equation, do you think? So a differential equation is an equation that involves one or more derivatives. What does it mean to solve a differential equation? Yeah, I think I know what you're saying, but see if somebody can articulate that. What's it mean to solve this thing? Look at our result here. We came up with the answer y equals 2x plus 2. Are there any derivatives in this equation? No. Okay, there's a big part of it.
What do you find like a trajectory? Like
So, okay, so it is, so I mean, that's in the language that we talked about. Yeah, it is. You're gonna either find a specific trajectory or a family of trajectories. Notice that the derivative disappears, so we've essentially undone the derivative, right? We found the function or functions whose derivatives obey the initial differential equation, right? That honor or satisfy the original differential equation. So what what function could we do this to and have it work?
All
Well, in this case, only that one,
Oh.
right? But if we remove that initial condition, then it would have been that whole family of curves, right? So when you solve a differential equation, you are essentially undoing the derivative, right? That's the whole goal. Okay, so what do we do? How do we undo something like this? Because our goal is to get from there to the antiderivative f of x plus c, right, to within some constant, okay? Here's kind of the process we can go through. Well, we can start off by writing this in differential notation, which is the stuff we most recently talked about, right? If we want to write this in differential notation, how do I write that derivative? Right now it's written as a ratio, dy dx. In differential form, it would be what?
Well, quotient rule,
I'm not asking for anything that complicated, but in differential form, a derivative looks a little bit different, right? In differential form, we don't differentiate with respect to anything, we just write the derivative as d something, right? So this would just look like dy equals what? In this case.
dx. Oh, fx times dx.
Yeah, so f of x
Oh, man.
times dx, right? So we put it into differential form, which just means we're gonna multiply both sides by dx, really all it means, right? Okay, and then to undo this thing, we're gonna apply this new symbol, this weird new symbol called integral. Okay, that's our calculus symbol for anti-differentiation. Or the word we're going to come to use eventually is integration.
Hang on.
Okay.
That was weird.
It is a little strange.
What's
Okay.
it called? Is that not
This is called an integral sign. Okay, this whole thing is called an antiderivative or an integral, and its job, the job of the integral or the antiderivative, is to undo differentiation. They are inverse processes, and so in the same way that if I were doing something like cubing, if I had the cube root of x, if I cube that in the same way that those functions cancel each other because they're inverse functions, these are inverse operations and they cancel each other. And so what I end up with is just y. That's how I solve the differential equation, is by doing this process. So I get y equals the integral or antiderivative of f of x dx, and we would describe that solution as the antiderivative f of x plus c. Okay, so now what is the anatomy of this thing? Let's describe, if we wanted to describe this weird equation that we've just drawn, what's the terminology that accompanies all this stuff? Ah, darn it. That's all right. Okay, what are these things? Okay, this is what we call the integral sign, and all it is a lowercase sigma, lowercase Greek s. Sigma is what we use, as you remember from pre-calculus. That's what we use. Uppercase sigma looks like this.
The big E?
Yeah.
Right. Okay.
The sum of all.
And it meant sum, didn't it? Okay, it meant a macroscopic sum, a sum of a discrete number of terms, right? Well, just like we've done with other stuff in calculus, remember that the Greek delta means change in, and in calculus that's kind of evolved to a lowercase d, which means microscopically small or infinitesimally small change in. This lowercase sigma, we're going to understand here, not today, but within a week or two, we're going to understand that as a sum of something. It can be the sum of areas, actually, but we'll get to that later. Okay, so that's the integral sign. This part inside right here, we call the integrand. That's like the argument of the function. That's what we're doing. We're trying to undo, right? In the cases we've looked at, the integrand has been, was 3x squared or cosine x. That's the function we're trying to play calculus Jeopardy with and anti-differentiate. Okay, and then this part right here, really, this is just what we call the variable of integration, or anti-differentiation. Spell that right? Yeah. Or integration. Okay? This is what we call the general solution. As we talked about, and this little guy is really important. This is what we call the constant of integration, or anti-differentiation. That is the most common source of mistakes for people when they first start doing antiderivatives, is they forget the plus c, but it has to be there every time unless you're finding a particular solution. It has to be there because we have to account for all those constants, all the infinite number of constants that could be there that would go away when we differentiate, right? Okay, so I think let's try a couple of these. And you're going to be better at this than you think already. Okay, so try that. So let's rephrase this as a calculus Jeopardy question. What are we really asking here? Yeah, that's really it, isn't it? The question is, the calculus Jeopardy question is, my derivative is 2x to the fifth. And we're trying to find the answer, what is the function, whatever, whose derivative is going to be that, right? We want the function whose derivative is that. Okay, so what did we get? Did we get an answer?
1/3 x.
What do you think? Right, what did you get?
1/3 x to the 6 plus c.
1/3 x to the 6
Plus c.
plus c. Okay, how would we check?
You take 6 by 3.
Take the derivative. Yeah, right? And are you now starting to realize that when you start to look at the potential for having to undo this stuff, the actual process of taking a derivative Pretty simple. Right? You just follow the rules to take a derivative. If I took the 6 down front, 6 over 3 gives me 2, doesn't it?
And 6 minus
Times
1.
x to the 6 minus 1 is 5. Yeah, that's it, isn't it? That's our answer. Okay, but wouldn't it be nice if we didn't have to scratch our heads so much every time we want to do one of these things and go through that whole process? Okay, so we're gonna, the first thing tomorrow, we'll come up with a way to get all the rules from our derivatives, and then we'll just go practice.